Hello all, hope you've been enjoying your break. Like I said on Friday, this online lesson, or video lesson, is going to explain how atomic radius, electron affinity, and ionization energy change as you go across a period, and down a group. Now, for this lesson, the controlling idea is going to be something known as Coulomb's law. Okay, and the Coulomb's law relates the force of attraction between two oppositely charged particles in an equation, and this is the equation below. Okay, you by no means need to memorize this equation. Okay, we just need to understand what the equation, or the relationships that the equation predicts, which we're going to discuss on the next slide. But just if you're looking at this equation, Q is charge, and D is distance, and F is force. Okay, so one of the things that Coulomb's law states is that the force between two oppositely charged particles is directly proportional to the magnitude of the charges. So basically, okay, if we're going to summarize this, the bigger the charge, the stronger the force. So if we're relating this to an atom, the more protons in the nucleus, okay, which are positively charged, okay, the more pull they have on the energy levels or electrons, which are negatively charged. And again, you should be writing all over this slide. Now, there's AP language for this, okay? And the number of protons in the nucleus, the more there are, it increases what is known as the greater nuclear charge, or Z effective, okay? So whenever protons are increasing in the nucleus, so you're increasing the number of protons in the nucleus, the AP exam likes you to say, okay, oh God, sorry. Let me try that again. So the AP exam wants you to say, as protons increase in the nucleus, they're exhibiting greater nuclear charge or greater effective charge. And you can abbreviate that with ZEFF. So again, more protons, it means greater effective charge or greater nuclear charge. Okay. Coulomb's law also states that the force between two oppositely charged particles is inversely proportional to the distance between those charges. So basically what that means, okay, is that the further the energy level is from the nucleus, the less pull or the less force they're experiencing from the protons pulling on the electrons. Because the electrons are now further away, so they're experiencing less pull, okay, from those protons because that energy level is further away. And again, there's AP vocabulary associated with this. So the AP wants you to say, as the distance between the nucleus and the energy level increases, the Coulomb's attraction between protons and electrons is reduced. Or the greater the distance, the less the Coulomb attractions between the protons and the electrons. So again, sort of the two controlling ideas here. More protons means greater nuclear charge, and they have more pull on the energy levels or electrons. And then the second idea, the greater the distance from the nucleus, the less pull the protons have on the electrons or energy levels. And those are going to be our two controlling ideas to explain the periodic trends that we're about to look at. The first trend we're going to look at is atomic radius. And the definition of atomic radius is the distance from the center of the nucleus to the valence electrons, to the last shell, or the last sort of orbital, or energy level in the atom. Okay, and again, essentially, it's how big the atom is. Okay. Now we're going to talk about how atomic radius trends as you go across a period. So as you go across a period, the atomic radius gets smaller. Okay, and the reason why is as you go across a period, there are more protons in the nucleus, which have greater effective charge, and then as a result, they have more force to pull the energy levels in. Again, this greater effective nuclear charge is the vocabulary that the AP exam wants you to use. So again, as you go across a period, the atoms get smaller because there's more protons and they have greater effective nuclear charge, and they can pull the energy levels in more. Now, this is easier. As you go down a group, each atom has another energy level, and then that energy level is further from the nucleus, and then the protons have less effective, less ability to pull because they have less Coulombic attraction because the energy level is further away. So they can pull on the electrons less, and therefore, as you go down a group, the atom gets bigger. So if we look at the questions that are here, it says, which of the following has a larger atomic radius? Explain why. And we're trying to look at the difference between K and Ca. Well, if you locate K and Ca on the periodic table, you'll see that they're in the same period. Okay, so you should have a periodic table out right now. So if you find K and Ca, and you'll see that they're in the same period. Okay, now, if you look at them, you'll see that Ca, they're in the same period. Ca has more protons than K. So because Ca has more protons, right, it's going to pull more, right? It's going to experience greater nuclear charge, and it's going to pull the energy levels in more. Okay, that greater effective nuclear charge is important. So therefore, Ca is going to be smaller than K, or therefore K is going to be bigger. Okay. Now, for down, we have K and Rb. If you locate K and Rb on your periodic table, you'll see that they're in the same group. Okay. Now, if we're trying to explain which one is larger, okay, the answer is that Rb is larger. The reason why is that Rb has more energy levels. Okay, and that energy level is further away. So because that energy level is further away, the protons have less coulombic force on the electrons, and they can't pull them in as more. Okay, if you did not write down those explanations, I would pause this video and re-listen to them and write them down. We're now moving on to the next trend, which is electron affinity. And electron affinity is the energy released or absorbed when a neutral atom in the gaseous phase gains an electron. So here we have an atom of F and an electron, and it's gaining an electron and becoming F minus. Okay, now, this is actually this is measured in kilojoules per mole, okay, which is annoying to measure. So scientists have made a measure that's related to electron affinity, or related to the idea of electron affinity, which is electronegativity, which is what we have talked about, and that is a measure of a neutral atom's likelihood of gaining an electron. And this is what we talked about in 10th grade. If you see the word electron affinity, know that it's related to electronegativity and has to do with how likely an atom is to gain electrons. Okay. Now, we're about to see that the trends that we're about to look at now for electronegativity and ionization energy are the reverse of the atomic radius trend. Okay, but let's look at them. So, if we're looking at electronegativity across a period, as you go across a period, the electronegativity increases. Okay? And remember, as you go across a period, okay, there are always more protons in the nucleus. So, there's greater effective nuclear charge as you go across a period. And therefore, the protons are able to pull in electrons greater. There's a greater attraction for electrons. Okay, and as a result, it's easier to gain electrons. Okay, so again, the key is this because there are more protons, there's greater effective nuclear charge as you go across, and therefore, as you go across, it's easier for atoms to pull in electrons. Okay, now as you go down a group, you must remember that as you go down a group, you're getting more energy levels. So as you go down a group, there's increased distance between the nucleus and the energy levels. And that reduces the coulombic attraction, or the force, that can be used to pull in electrons by the nucleus. And as a result, it's less likely to gain an electron. Okay. So if we look at the learning check here, it wants to know which one has a higher electronegativity between Na and Cl. Well, Na and Cl are in the same period. Okay, and again, as you go across a period, the number of protons increases. And you'll see that Cl, if you look at your periodic table, is more over in the period. So because Cl has more protons, okay, it can experience greater effective nuclear charge, okay, and is because there are more protons, and is better able to pull the electrons in. Okay, which is what electronegativity is, the desire to gain electrons. If we're looking at the difference between O and S, this is in O and S are in the same group, and you'll see that S is further down in the same group. Okay, so what that means for S is that S, the distance between the nucleus and the last energy level, is greater. Okay, so because those electrons are further away from the nucleus, those electrons experience less coulombic attractions, and it's harder for the nucleus of S to pull in the electrons in order to gain them. Okay, again, if you didn't write those things down, okay, I would pause the video, listen again, and write them down. the last trend we have to look at is ionization energy. And you should have this ionization, the word energy should be here. And ionization energy is the energy needed to remove an electron from the outermost energy level of an atom. So here we have sodium, and we'll see that we're taking an electron from sodium, and it's becoming sodium plus 1. Okay, so that is the sort of what's happening when you're, so the ionization energy is the energy needed to do this reaction. Okay, now we're going to look at the trends. So as you go across a period, it increases. And again, the reason is, as you're seeing a trend, is as you go across a period, there are more protons. So, there is, as we've said a million times at this point, greater effective nuclear charge. And because there's greater effective nuclear charge as you go across, there's a greater attractive force between the nucleus and the electrons, and it's harder to take them away. Again, because it's ionization energy, the energy needed to remove an electron. Okay? So again, like that's what I just said, more energy needed to pull away the electron. Again, it's all about, in period, it's all about greater effective nuclear charge because the protons are increasing. Okay. Now as you go down a group, okay, once again, there are more energy levels. So, the distance between that nucleus and the last energy level is greater, okay? So therefore, since that nucleus is further away, that nucleus on those protons or have less force on those outer electrons. Okay, again, that reduces the coulombic attraction between the nucleus and those electrons because of the distance, okay? And as a result, because those electrons are further away, okay, less force on them, it's easier to pull away the electron, or less energy is needed to do it. So that's why it decreases. Alright, now for our last learning check here. So if we look at Ca and Sr, we'll see that Ca and Sr are in the same group. Okay. Cr is located higher in the group, right? So it's higher up in the group. So what that means, okay, is that the electrons in Ca are closer to the nucleus, okay? And because there's less distance, okay, there's greater coulombic force on those electrons. And as a result, it's harder to pull them away. And therefore, you have to exert more energy to pull them away. So Ca has the higher ionization energy. Okay. Now, if we're looking at the distance so the difference between Ca or K, you'll see that Ca and K are in the same period. Okay. And again, Ca is going to have the greater ionization energy. The reason why is that because it has more protons, okay, and because it has more protons, the outer electrons experience greater effective nuclear charge, okay, and because of that greater effective nuclear charge, okay, there's more pull on those electrons from the nucleus, okay, and therefore it's harder to pull them away than it is in K, which has less protons. And again, ionization energy is the energy needed to remove an electron. Okay. So now we're going to look at something called second ionization energy, which is the energy needed to remove a second valence electron. And it's always higher than the first ionization energy. If you look at here, here's sodium, and this is the energy needed to remove one electron from sodium. And you'll see here there's a huge jump up in the amount of energy to remove the second energy level, the second electron. And the question is why? Well, if you remember, sodium has one valence electron. So once it loses that one valence electron, which is in the third energy level, you're then taking the second that next energy level, or that next electron is then in the second energy level. Okay, and that electron is closer to the nucleus. So once again, it's experiencing greater force. Okay, and that's why you see that this jumps up so much. This is like in the third energy level. It's the valence electron. Okay. And then when you're removing the second energy level, you're removing the second electron, you're removing it from the second energy level. And you'll see there's a huge jump up in energy there. Now if you look at Mg, you'll see that the big jump here doesn't actually occur at the second ionization energy. It occurs at the third ionization energy. Why is it different? Well, magnesium has two valence electrons. So the first electron that you remove, you're removing from the third energy level. And the second electron that you remove, you're also removing from the second energy level. Okay, but that third electron, okay, is in the second energy level. So we have these that are in the third. I might have said that wrong. These are in the third, the first valence electron, and the second valence electron. But when you remove the third electron, this is now in the second energy level. Okay, so now that energy level is closer to the nucleus than the third, so there's greater force. and therefore greater ionization energy needed to pull away that electron.